Hello everyone. In this lecture, I shall discuss the improper integral of first kind. If we recall the definite integral, what you read in your 12th class, suppose you are given a function f of x and you are asked to integrate within the finite limit a and b, right? If the limits is finite, a and b both are finite, and this given function doesn't tends to infinity at any point in the interval, and what we call the function is bounded. That means f is bounded. Okay, f is bounded. Then you know how to evaluate the integral. It is, suppose the integration of fx is capital Fx, then the upper limit is a and lower limit is a, upper limit is b, and f of b upper limit minus f of a lower limit, and this will be a finite value, right? And you evaluate to get this interval only when the integral exists, right? So now any deviation from this, if any deviation from this will occur, means either this is not finite or this is not bounded, then it will leads to the improper integral. For example, if the limit is not finite, then it leads to the first kind integral. If a is minus infinite and v is here infinite, right? Or simultaneously both this, right? But fx is bounded, right? So before discussing the details of this integral, let me to introduce myself, Professor Sushant Kumar Paikray, currently working as a professor in the Department of Mathematics, Bir Surendra Sai University of Technology, Budla. So many of my students requested me to prepare video lectures on some important topics for their benefits, and I too motivated to prepare some lecture series. So now coming to this improper integral of first kind. So here the limit of the integration is infinite, but the integral is bounded, right? That means the function will not tend to infinite at any point in the given interval. For example, if I say integral sum minus infinity to a minus infinity to some b f dx, right? Or I say suppose some a to infinite f dx, or I say some minus infinity to infinity f dx, right? F dx. So these are all here. Here you note that f is bounded, right? F is bounded, right? Then this type of integral are referred to the integral of first kind, right? But coming to the second type integral, here the limit is finite. The limit of the integration a and b both are finite, right? A is finite, b is finite, both are finite, but f is unbounded. You mark this is unbounded, means f tends to infinity, right? F tends to infinity at some points or any one point in the interval ab. It may be at the end point lower end a, it may be at the upper end b, or it may be at any point in ab. For example, if I say integral 0 to 1 dx by x, so I can say unbounded at a, unbounded at the lower limit 0, is not it? If we substitute 0 here, then the integral will not exist. If I say integral from 0 to 1 dx by 1 minus x, then what will happen here? At 1, this is unbounded. This means it is unbounded at 1, is not it? So it may be unbounded at some intermediate point also. If I ask you integration from 0 to 2 dx by x minus 1, right? So here it is unbounded at 1. So this 1 is in here 1, 0, 0 and 2, right? It is in the intermediate point. Or it may be unbounded at both 0 and 1. If I say dx by x into x minus 1, it is unbounded at 0 and 1. So this type of thing will occur. It is not limited to only 0 and 1, any limit, but the limit is finite. Now what is a third type of integral, right? Improper integral of third kind. So what is third kind improper integral? Improper integral means it is a combined case. combined case, right? Combined case of 1 and 2, 1 and 2, right? Means here limit is infinite. If I say some integral 0 to infinity dx by root x, what will happen here? You see here, so because of infinite it is first kind, because of infinite it is first kind. Now because of 0 it is unbounded, it is second kind. So it is a case of the third kind improper integral. If you think of another example, suppose I say integral 0 to 1 e to the power minus x. You say integral 0 to infinite e to the power minus x, x to the power n minus 1 dx, right? X to the power n minus 1 dx. Now how to evaluate the improper integral? Now we'll see how to evaluate the improper integral. We can evaluate the improper integral, evaluation of improper integral. Evaluation of improper integral. Let me to recall you some background of limit. If I ask you 1 by 0, then what is your reply? What is your reply? We can say rather it is undefined. Undefined. Why it is undefined? It is undefined because the denominator is 0, is not it? But the moment I say what is limit extends to 0, 1 by x, right? In that case we will say the answer is infinite. Here we say not possible. Here we say not possible. But we make it possible. By the limiting approach. So similarly, I say what is limit extends to infinity 1 by x, right? It is here 0. So this infinite, when there is a infinity is there, and when the denominator is undefined at a particular point, we can deal with those cases by using the limiting case. Similarly, to evaluate the improper integral, suppose I ask you to evaluate integral e to the power minus x dx some 0 to infinity, right? I ask you to evaluate it. So how to evaluate it? So if we evaluate it, it is integral 0 to infinity e to the power minus x by minus 1, right? The limit of integration is, if you evaluate this integral, and the limit of integration is 0 to infinity, and here it is minus e to the power minus x. So now putting the upper limit, it is e to the power minus infinity is 0, and e to the power 0 is here 1. So this is equal to 1. So we call this integral converges to 1, right? This integral is converges to 1. So when there is the question of infinity, right, then there is a question of the convergence here, right? So now but this way is not the correct approach here, right? It is not exactly the correct approach. Not exactly the correct approach. As I told you here, this case, and I told you here this case, it is not exactly the correct approach. But the same thing we are doing in a limiting sense, we are using the limit here. So we'll write it 0 to infinity e to the power minus x dx is equal to limit some b tends to infinity e to the power here 0 to b e to the power minus x dx, right? Then we are limit b tends to infinity, it is e to the power minus e to the power minus x 0 to b. So this is equal to here minus of, this is limit of b tends to infinity e to the power minus b minus 1, right? E to the power minus b minus 1. But when limit b tends to infinity, e to the power minus b will give you 0. So this is of minus of 0 minus of 1 is 1. That means to deal with the infinite case, right? To deal with the infinite case, we will use the limit. So this is the correct approach here, right? This is the correct approach here. So this definite integral, this definite improper integral here can be ruled out by using the limit concept. Similarly, means if I ask you your integral 0 to b f dx, how to overcome it? It is 0 to infinity. How to overcome this? It is equal to limit b tends to infinity, here 0 to b f dx. Similarly, if I ask you integral minus infinity to some k f dx, then how to evaluate it? So this is limit some lambda tends to minus infinity, here lambda to k f dx. In that way we will evaluate it. In case of minus infinity to infinity f, we will split it to some minus infinity to some c plus some c to some infinity. Then we'll overcome it by using these aspects. We can overcome it. For example, one more important thing I will say. Suppose I will say integral minus infinity to 0 e to the power x dx. So how to deal with this? Here you put x is equal to your minus y. So that means your dx is equal to your minus dy. So when minus infinity less than x less than 0, right, means here infinity less than y less than 0. So this integral will be here minus of e to the power minus y dy with infinity to 0, right? And it will be here this, for this minus sign we reverse the limit 0 to infinity e to the power minus y dy. Is it not the same thing as 0 to infinity e to the power minus x dx? So by this previous argument, and is it not your 1, right? So that means this infinite minus infinity, right, can be converted back to plus infinity with this substitution x is equal to minus y, right? Later on we'll implement some test on this, and this test will be bring back to minus infinity to infinity with this substitution, right? So I will tell you a standard test here. You see, in many cases what will happen, in many cases for some direct evaluation, let me to tell you some direct evaluation, let me to tell. Suppose I ask you evaluate integral 0 to infinity x square e to the power minus x dx. So how to evaluate it, right? So that means ignoring the limit, we will first evaluate this. This is really we want to apply the by parts of integration, But if you apply the by parts, 2 times by parts will be needed here. But we can overcome it. Suppose you are asked ub dx. How to overcome it? One is your algebraic, other one is suppose your exponential or trigonometric. So then you keep the first function silent, you integrate the second function once, then put a negative sign, differentiate the first function once, and integrate the second function twice, put a positive sign, twice differentiate the first function, thrice integration the second function, and minus, first one is plus, then minus, then plus, then minus alternatively till this derivative term, algebraic term, means it comes to 0, right? If we apply this easy way of integration, then it is quite easy to integrate it. So let me to apply this way of integration here. So this is equal to, if I integrate it here, so this integral will becomes, so let it be my I. So my this integral I becomes x square, remains silent, integration of e to the power minus x, minus e to the power minus x by minus 1, put a negative sign, the derivative of this is 2x, and integration of this, right, integration of this means original one is integrated twice, it's same thing as this is already integrated once, we integrated once more, so it is e to the power minus x by minus 1 into plus 1, minus 1 into minus 1, then you differentiate it here. So it is put a positive sign here, it is 2x, and the integration of this here, right, the integration of this here e to the power minus x by minus 1, right, minus 1, and the integral, right, and it is better we should write it in this way. So we should better, we will write it fast. It is some limit, some lambda tends to infinity, some 0 to lambda x square e to the power minus x dx. It is better to write like this. So some limit lambda tends to infinity, it is some 0 to lambda, right? In that way you write it. So what will happen here now? Right, what will happen here now? You know, e to the power minus infinity is 0, right? Anyway, this term will come to 0. This term will also come to 0 because e to the power minus infinity is 0, right? Limit lambda tends to infinity, e to the power minus lambda is here 0, and right. So this lambda will not work here. This lambda will not work here. So what will work is, so that is equal to, we have a negative sign here, so this is equal to minus of, right? It is then it is minus of plus of 2. The derivative of 2x is plus of 2, so it is minus of, right? Putting e to the power minus infinity is 0, right? And putting here 2 is here, putting 0 is e to the power 0 is here 1, so this is equal to 2. So therefore this integral is converges to 2, right? So we can say this integral, the integral 0 to infinity x square e to the power minus x dx is convergent to 2, right? Is convergent to 2. Or we can say integral 0 to infinity x square e to the power minus x dx converges, right? Converges to 2, right? We may write is convergent, or we write converges to 2. In that way we will evaluate the integral. Similarly, if some cases are given, I may recall you some of the standard integration formula, e to the power ax sine bx dx. Then what is the integral? E to the power ax by a square plus b square a sine bx minus b cos bx. If some limit will be given to here 0 to infinity, then accordingly we can do it. Limit some lambda tends to infinity, right? It is here 0 to lambda, and we can overcome it. Similarly, some other type of integral, suppose it is asked integral 0 to infinity e to the power x cos bx dx, right? Cos bx dx. Then what is the integral then? So it will be again the formula of integration here is, right? The formula is e to the power x by a square plus b square a cos bx plus b sin bx, right? So this way of integration, right? My intention is to say you here the integration of this is this. My intention is only to say the formula. So this formula will help you for direct evaluation of the integral. If I ask you one more example, suppose evaluate integral 0 to infinity dx by s square plus x square. You want to evaluate it. So you will write it. Limit some lambda tends to infinity 0 to lambda dx by s square plus x square. So this is equal to some limit lambda tends to infinity. So this is 1 by s square plus x square. The integration is 1 by a tan inverse x by a. Is not it? So here limit is from 0 to lambda. So this is equal to here 1 by a tan inverse lambda here. So this tan inverse lambda is an infinite. Tan inverse infinity will give you pi by 2, and tan inverse 0 will give you 0. So this is pi by 2a. So therefore we say this integral converges to 2a. 1 pi by 2a, right? Pi by 2a. But the tragedy is that, so what is the tragedy is that? The tragedy is that many times it is not easy to integrate, right? After long integration, we see what is the answer. The answer is infinity, means doesn't exist, and in this case we say it is divergent. Once it is divergent, right? Once it is divergent, then what is the use of this lengthy approach, right? What is the use of this lengthy approach, right? Why we'll have this lengthy approach? to say that it is divergent, right? So we should first go for the test of convergence, right? Sometimes it is asked test of convergence, right? What are my test of convergence? How to test the convergence, right? Means there are some standards test here. If I say one test one integral 0 to infinity e to the power minus rx dx is convergent, I write convergent. In short I am writing CGT, and for divergent in short I am writing DGT. Is convergent if here R is convergent if R is here greater than 0, right? This R is greater than 0, and is divergent is divergent, right? If R less than equal to 0, right? For example, if I say integral 0 to infinity e to the power minus x dx, right? As you did it earlier. So what is R here? R is equal to here plus 1, is not it? E to the power minus rx, you see. So R is here plus 1, right? Is it not here greater than 0, right? So we say this integral is convergent. Therefore we say it is convergent. This integral is convergent. Now if it is asked what is the sum? What is the sum now? What is the integral value? Then only we evaluate it. If it is asked that just go for the test of convergence, then we need not have to evaluate the details. If I ask integral 0 to infinite e to the power root x dx, then what will happen here? Root x dx, if you compare it with minus of r into x, right? Then what is your r here? R is here minus half. Is it not less than 0, right? So what will happen here? It is divergent here. If I ask integral 0 to infinity e to the power x simply, then what is r here? R is minus 1 here, right? Is it not here less than 0? If I simply ask 0 to infinity dx only, is it not here 0 to infinity e to the power 0 into x here? Is not it? So means r is equal to 0 here. It is a divergent, right? So this test. So instead of evaluating the entire integral, we just apply this test. We can extend this similar test, other test, to evaluate the integral to know whether it is convergent or not, right? Coming to another standard test is your P test. Another test, let me say the second test is my P test. What is the P test now? So coming to the P test, if I say integral a to infinity dx divided by x to the power p. So here a is positive, right? A is positive. Now we say this is convergent. We say this is convergent if p greater than 1. If p greater than 1. And we say it is divergent. And we say it is divergent if p less than is equal to 1, right? This will be a great help if I ask you some integral 1 to infinity dx by x square. Then we see here a here is 1 here, so it is positive here, right? Then we can say what is p here? Here p is here 2, which is greater than 1. So this integral is convergent. If it is asked to test for convergence, then we just go for the test rather than the whole integration. If I ask here integral some 1 to infinity dx divided by some root over of x here. So here what is p here? P is equal to here half. So it is here less than 1. Is not it? So this integral is divergent, right? This integral is divergent. So this P test is a wonderful test to overcome many problems, and later on this will help you in comparison test to evaluate it. Then the next test is coming to the third test is the mu test. Is the mu test, right? This mu test is again another important test for algebraic function. Now coming to the another important test, that is my mu test, right? Mu test. So what is the mu test? Means f is continuous and integrable in the interval 0 to infinite, right? 0 to a to infinity, a to infinity. But this is the background. We don't bother about this, but we bother about this. There exists a number mu, and if this number is greater than 1, you see it. If this number is greater than 1, and this limit extends to infinity, this is a finite number, means exist and is finite. We don't bother whether it is 0 or not equal to 0. We don't bother, or not equal to 0. We don't bother about this. Means if it is a finite value, it is a finite number, 0 or non-zero, then we say this integral is convergent, right? This integral is convergent. Clear? So here generally the lower limit of a, the lower limit a we are taking is positive, right? Is positive, the lower limit. Clear? Now the question is, what will happen for mu less than is equal to 1? For mu less than is equal to 1, if limit extends to infinity, x to the power mu fx is some finite value, is some a is not equal to 0, right? This a is a finite value which is non-zero again, which is non-zero, right? Finite value which is non-zero or plus minus infinity, anything, right? Then we say this integral a to infinity f dx is divergent, right? Divergent, right? So what will happen? So here mu is less than is equal to 1, and this limit is a finite value, but this value should be a non-zero value. This value should be a non-zero value, or it is plus infinity or minus infinity. Then we say this integral is divergent. Means if your a is equal to 0 here, in this case, if a is equal to 0 here, then test fails. Right? But here if this value is suppose my a, we don't bother. A may 0, a may not equal to 0, any finite value, we don't bother, any finite value. Then in this case, the integral is convergent here. So let me to solve one example. Now how mu is taken? Now remark how my mu is taken. Mu is the difference of highest power of x in denominator minus highest power of x in numerator, right? Basically that means this test will work for algebraic function, right? For algebraic function, basically we apply this test for algebraic function. Coming to an example, suppose you are given integral 1 to infinity x by 1 plus x square dx. If I ask to integrate it, right? If I want to integrate it direct way, then you put the denominator 1 plus x square is equal to t. So implies here x dx is half dt. In that way, you substitute it and you go on integrating. But the moment I apply the test here, So what is my mu here? The power of the denominator power is 2, right? the maximum power of the numerator power is 1 here. So I take my mu is equal to 1 here. So mu is equal to my 1 and I apply limit x tends to infinity. Here x to the power mu into fx. Limit x tends to infinity. Here x to the power mu into fx. So this will be my limit x tends to infinity x into x by 1 plus x square. So while evaluate the infinite limit, we divide the highest power in the numerator and in the denominator. In the numerator it is x square, I take common, it is 1. In the denominator, if I divide and multiply by x square, this will give you 1 and this will give you 1 by x square. Now this x square and x square cancel. It will give me 1 by 1 plus 0 is equal to here 1 by 1 plus 0. So this is equal to here 1. Right, this is equal to here 1. Now you see, it is a second case here, right? But we are taking mu is 1. It is a case of mu less than is equal to 1. It is a case of mu less than is equal to 1. And another thing we note that this a here is not equal to 0, right? So this limit is a finite value not equal to 0 and this mu is less than 1. So what will happen? Therefore this integral 0 to here infinite, right? This integral, the limit was given 1 to infinity, right? 1 to infinity x by 1 plus x square dx is divergent. So once it is divergent, the answer will go to infinity or the answer will go to minus infinity, right? So here if you evaluate it, so after a long evaluation, the answer will give you infinite here. The answer will give you infinite here or minus infinity. In fact, here this answer will give you infinite, right? So what is the once the integral is not convergent, then what is the need to have these lengthy evaluations? This one line test will say you whether this integral will converge or diverge, right? Now coming to one more important question I will tell you. Suppose here suppose you ask you one more integral. This is an important question here. 1 to infinity dx by x. Test, the instruction is test the convergence. So you see here, we decide to go for the mu test here, right? We decide to go for the mu test. So what is the power of the denominator here? The power of the denominator is 1 by 3 plus 1 by 2. Minus the power of the denominator is a constant, means 0, the power is 0. So if you add it, the LCM is 6, it is 2 plus 3 is 5 by 6 and it is less than 1, right? Less than 1. So we now apply the limit x tends to infinity, x to the power 5 by 6 into your given function fx, 1 by x to the power 1 by 3 into 1 plus x to the power half. This half is here, this x to the power half is here, x to the power half, right? So now for infinite limit we are taking the highest power of x common. So in the numerator is x to the power 5 by 6 is fine. Now in the denominator it is x to the power 1 by 3 is here. We take common here again, means we multiply x to the power 3 by 2, multiply x to the power half and divide x to the power half here. So it is 1 by 3 plus 1 by 2 is 5 by 6. Now this becomes my 1 and this becomes my 1 by x to the power half. So now as x tends to infinity, 1 by x tends to 0. This and this cancelled. So this will give you 1. This is your a and it is not equal to 0, is not it? You see. So now you come to this test here. So thus you see the integral is divergent here. You see here, I have told you this is a is not equal to 0, right? Mu is less than equal to 1, then this integral is divergent. Okay, so here you see this integral is the moment you are getting mu is smaller than 1, right? The moment you are getting mu is smaller than 1, then we go for the think of the divergence, right? For which we need the value a is not equal to 0. So therefore the integral is divergent here, right? Divergent by mu test, Now coming to another important test is my test 3, say it is my comparison test, right? Comparison test. We'll compare the test, means any function larger than the convergent function, right? So function smaller than the convergent function, we say here you are given a function means smaller than convergent function. We have a function f here, we have a function g here. Now the moment this g is convergent, right? If this is convergent and this is a smaller function here, then this implies, right, this must be convergent. Now the moment this is a larger function, the moment this function is divergent, if the moment this is divergent function, right? If the smaller function is divergent, you see the function smaller than a convergent function. You see now, suppose you are given, and it is as usual, f is belongs to a class of continuous function in interval, means the integration permits here. So now if f is smaller than g, then once g is convergent, then smaller function is also convergent. So convergence of g ensures the convergence of f. Now similarly, if g is here smaller than f, g is smaller than f, so f is a larger function here, right? Then once g is divergent, it is superior to divergent, right? Then it is divergent. So here once this d is divergent here and this is larger than the divergent, right, means divergent, right? Larger than divergent is divergent, larger than divergent is divergent. Clear? Now smaller than convergent, here we can say smaller than convergent is convergent, but larger than convergent, smaller than divergent, in between we cannot say. No conclusion, right? No conclusion can be drawn from the convergence of these functions. This is a powerful test, and the reversion of this test is, right, if we have here fx by gx, some limit extends to infinity, is a finite and non-zero, non-zero, then f and g behave alike. F and g behave alike means both will converge together or both will diverge together. If you ask you now one question, suppose you are asked integrate from 1 to infinity, right? But here the limit of integration we are taking, 1 to infinity, here sine x by x square, right, dx. You see, so this is a function here, sine x by x. You know, sine x by x square, modulus of sine x is always less than 1, and x square is x square here. So now you see here. So now if I think this is my gx now, so what will happen to 1 by x square now? 1 by x square 1 to infinity dx is convergent, is not it? Is convergent because it is p test. P is equal to 2, which is greater than 1. So by test this is convergent. So once this is convergent, so this will definitely convergent, is not it? So this will definitely convergent. That means I can write it like this: 1 to infinity sine x by x square dx is like a smaller than I can say 1 by x square dx from 1 to infinity. The limit of this is smaller than the limit of this. Now this is convergent by p-test. By p-test, is not it? P is equal to 2 greater than 1. So once this is convergent, it is smaller than a convergent function. So convergent integral. So therefore this is convergent. In this way, we will evaluate it. Similarly, we have some further examples. Coming to some more examples. Coming to this integral a to infinity cos x by 1 plus x square. Right. So this is my f now. If I take some my g, right, here cos x by 1 plus x square. So is it not less than my 1 by 1 plus x square? Maximum value of cos is 1. So since x is positive here, is it not less than 1 by x square? Because this denominator is large, this denominator is small. So this is a larger function here. Right. Now what will happen to this? This is my g. This is my g. What happens to my g now? A to infinity 1 by x square dx is convergent. Why? P is equal to 2 greater than 1. So once this is convergent, so this implies this will convergent by a comparison test. Comparison test. It's not it. This will convergent by comparison test. Likewise, suppose you are given another question. Question number 2, you are given this. Let it is my f. Let it is my f. Let you take here g is equal to some 1 by x square. Right? 1 by x square. So what will happen? F by g. So this is equal to, it is your x square by 1 plus e to the power minus x into x square. Is not it? So now I take limit x tends to infinity this. Is your limit x tends to infinity this. Now this and this cancelled. This will give you 1 by 1 plus 0 is 1. So it is finite, not equal to 0 and finite. So therefore what will happen? So therefore f and g will behave alike. F and g will behave alike. By comparison test. Is not it? So this integral here. So this integral here is this integral g. Integral of g here is what? This integral is convergent. This is square. This is convergent, right? Because p test, p is equal to 2 greater than 1. So this is convergent, means this is convergent. So clearly what we conclude here? So we conclude here is integral 1 by 1 plus e to the power minus x into x square and 1 by x square behave alike. So therefore it is 1 to infinity. This is being divergent, this is being convergent. So this is being convergent, so this is convergent. Right? You should write, arrange it and write. Okay? In your own language you should write it. Now coming to this integral. In this integral you see here the power of x is 1 and here the power of x is 3 by 2 because the root over is there. So I want to make a 1 by root x. Let this total is my f. This total is my f here. Right? Let I choose my g is my 1 by root x. Right? Means here the power of x is half and this power is 1. Then this power becomes a 3 by 2 because the denominator power is x to the power 3 by 2. So f by g if I take, then what will happen? It is x into root x, is not it? Tan inverse x by, here denominator will be here. Here the denominator will be tan inverse x and your denominator will be, you take common x to the power 3 by 2 and this will give you 1 and this will give you 4 by x. 4 by x here and the root over is here. Is not it? 4 by x here. The root over is here. 4 by x to the power 3. Right. So now what will happen? This is your x to the power, this is your x to the power 3 by 2. So x to the power 3 by 2, 3 by 2 cancelled here. So this is when the limit x tending to infinity, limit x tends to infinity. So this will give you what? This is limit x tends to infinity, tan inverse x by here 1 plus 0 root over. Now tan inverse pi by 2 is here, tan inverse infinite is pi by 2, right? It is pi by 2. So what will happen? It is finite. It is finite and not equal to 0. So therefore f and g behave alike, is not it? So therefore f and g behave alike. But what happens to this integral g? Integral g here 1 to infinite. Integral g 1 to infinite is what? Is integral 1 to infinite 1 by root x dx. So p is equal to your half is less than 1. So this is divergent. So therefore integral of f, given integral 1 to infinity dx is divergent, right? So this is divergent by comparison test. So you should adopt this way of integration. The comparison test is a wonderful test to overcome this. So this comparison test is the fourth test, right? Now the fifth type case is a mixed case. If the test fifth is a product case, it's a product case here. Suppose your integral a to infinity fx into pi x dx is a product case here. Then we apply, there are two approaches here. We apply the Abel test. Abel test will apply, and another test is Dirichlet test. These two tests will help you to overcome the problem in a very easy way. So let us have some standard examples. Coming to another important test is your Abel test to deal with the product function, right? Means you are asked to evaluate the integral of this form, right? Means you are given a product form. So we see what happens to f. So now if this f is individually a to infinity f is convergent by the earlier technique, we already done it earlier. Test 1, 2, 3, 4, 5, test 1 to 4 we apply here, and we see whether it is convergent or not. And we see the second function here, right? So this is 1 and plus this second 2. If these two will hold, right, then this product function is convergent. For example, suppose you are given e to the power minus x and sin x by x square. Let I call it my f, you call it my pi, right? Then what will happen here? As we did earlier, what happens to your f? As we did earlier, this pi here, this f integral a to infinity sin x by x square, right? Is it not smaller than here dx by x square as we did earlier, right? A to infinity. So here it is here g, it is convergent by p test. P is greater than 1. So therefore this is convergent. So our first property, that f is convergent. And what happens to this? You know, e to the power minus x is decreasing function, right? When x tends to infinity, e to the power minus x tends to here 0. So this function, right, is bounded by here 1, bounded by here 0, right? The maximum value of this function is this. So this function is a monotonically decreasing function and bounded, is not it? Bounded. So therefore, so you should write it clearly, e to the power minus x is monotonically decreasing and bounded, and integral a to infinity sin x by x square dx is convergent. Therefore by Abel test, integral 0 to infinity, not 0, it is greater than 0, a to infinity, here e to the power minus x sin x by x square is convergent, right? This is your Abel test. Now come to another important test, is the Dirichlet test. Now coming to another important test is the Dirichlet test. What is that Dirichlet test? It is again deal with the product function. If you are given a product function fx and phi x, product is given. So now we have to see this function f. This function f is bounded and monotonic, right? And this limiting value is 0. This limiting. So in view of this, what it usually indicates, this should be a monotonically decreasing, then this limit will come to 0. And secondly, this integral is bounded. This integral is bounded means we'll find that this is some less than some k, right? This is third. If this 1, 2 and 3 holds, right, then only we say this product function is convergent. Now coming to this integral. So coming to this integral, let it be my f. Let it be my f now. And let it be my phi now. So what will happen to my f? Right, f, you see the denominator is larger than the numerator in this interval. So f gradually decreases, is not it? So it is monotonically decreases. And you find it, limit extends to infinity, x by 1 plus x square. The denominator is x square is larger here, right? So infinity will come in the denominator. This integral is 0 here, it's not it? This integral is 0 here. So condition 1 satisfied and condition 2 satisfied. This is monotonic decreasing and bounded also, right? So here, and what will happen to integral phi x, integral of phi x dx, some a to x modulus. So this is equal to some integral a to x sin x dx modulus. So integration of sin x is my sum minus of cos x with my limit is from a to infinity, a to x. So it is equal to my minus of cos of x. It is minus of minus plus cos of a. You see, it is less than, I can say maximum value of cos x is 1 plus this is here also 1, I can say maximum is 2. So therefore what will get? This is here bounded. We don't need what is the exact thing. We just see that whether it is bounded or not. What is the bound we don't need to find, and we see it is bounded. So clearly what we get? Clearly what we get? X by 1 plus x square, right, is monotonically decreasing. F is equal to this is monotonically decreasing and bounded, and integral phi x dx sum from a to x is equal to integral a to x sum sin x dx mod is also bounded, Therefore by Dirichlet's test, the given integral is convergent. The given integral a to infinity or 1 to infinity x by 1 plus x square sin x dx is convergent, right? So these two tests are wonderful tests to deal with the product function. Let us see one more example. Integral 0 to infinity. Basically we need this should greater than 0, a should greater than 0, but since this is here 0 here, we split it in this way from 0 to some 1 say or a say and plus some a to infinity say sin x square dx, and it is sin x square dx. Now it is a proper integral. And it will give you a finite value, right? Now we want to readjust it. Since it is x square, the derivative x square is 2x here, and to balance it we need to multiply 1 by 2x here, right? Now we split which is f and which is g, you see. So let it be my f here, and let it be my phi here, right? So looking into this situation, we'll decide which is f and which is phi. So what happens to your f? F is 1 by 2x. So gradually it will decrease, right? It will decrease and it is bounded. is not it? Now what will happen to integral some a to x 2x sine x square dx? If I put this is some t, so this 2x dx is dt, so it will have the form again sine of x square a to x sine of t, means t is my sine t dt I say, so we will get it of this form. So what will be this integral? Likewise the previous case, it is cos x, right, from a to x, so it is less than cos x plus cos a, right, means this is less than 2. We don't bother about this, this is a less than equal to, means this integral here phi is bounded here, right? So therefore f is monotonically decreases and bounded, and integral a to x phi dx is bounded, right? So therefore, so both the integral, this first integral, let it be my I1 and let it be my I2, right? So my I2, so therefore my I2 is convergent here. So therefore the original I is I1 plus I2 is give you a finite value now, right? Finite value. So by Dirichlet test, it is convergent. It is convergent. Now let me to tell you some important questions. So let us solve some important examples. So you are given 0 to infinity. Let's sum, this will be greater than 0. Sine square of x by x square. Let it be my f. If I consider my z is 1 by x square, you see now sine square x by x square. So sine square x is less than equal to 1 maximum value, and it is 1 by x square. So what happens to this integral z 1 by x square dx from some 1 to infinity, from 1 to infinity is here convergent, is convergent. Why? Because p is equal to 2 greater than 1 by p test. Once this is convergent, so by comparison test, therefore by comparison test, right, your integral 1 to infinity sine square x by x square dx is convergent, right? Now coming to this, and we are going to apply here the mu test. So the denominator power of x is this is half. So the denominator power is I have told you 1 by 3 plus 1 by 2. So mu is this minus my numerator power is 0. So it is 5 by 2, 5 by 6. So here the mu test, limit x tends to infinity, x to the power 5 by 6 into fx, 1 by x to the power 1 by 3 into 1 plus root x. We did it earlier. So this is limit x tends to infinity, x to the power 5 by 6 by here x to the power 1 by 3 and x to the power half taken common. 5 by 6, this will give you 1 and this will give you 1 by root x, right? So this and this cancelled. So this will give you here 1, right? Which is here not equal to 0, and this mu value is less than 1, right? Mu value is less than. So this is a divergent by mu test. Divergent by mu test. Is not it? Divergent by mu test. Coming to this problem, right? Coming to this problem, let it be my f. Let it be my phi, right? Let it be my phi. We don't bother. We may take it a for phi, or we may take this is phi. We may take this is at no issue. That depends upon the convenience here. So here what will happen? Here phi is here. You see, e to the power x is a decreasing function, right? E to the power x is decreasing. E to the power minus x. And here 1 minus phi is 1 minus e to the power minus x is an increasing function, right? When this will decrease and 1 minus this will increase. Anyway, this is a monotonic function. Monotonic. We may write increasing or decreasing, that doesn't matter. Increasing function. and is bounded also, bounded, because this value is maximum value is 0 here, right? E to the power 0 is 1, e to the power minus infinity is 0, right? Now this is a bounded function anyway. Now what will happen to this integral? Integral of f dx, as I have told you. So this cos x by x square mod is less than here 1 by x square. So now this 1 by x square is convergent, right? So therefore this integral is convergent. So therefore their product, therefore phi f, this product here a to infinity is convergent. It is because of by your Abel test, is not it? So now coming to the fourth integral, can you not write it? A to infinity 1 by root over of x into your sin x. Let it be your f and let it be your phi, right? Let it be your f and let it be your phi. So what will happen to this? So this 1 by root x will gradually decrease, and also it is bounded here, right? It is bounded here. So f is monotonically decreases, or we will just write monotonic and bounded and likewise if I say some a to x sin x dx mod, so integration of sin x is minus cos x from a to x mod dx. So this is less than here some it is here cos x plus cos a, it is less than 2 anyway. It is also bounded, right? It is also bounded, right? It means this is bounded. So here this is bounded, here phi is bounded here. So these two combinedly will give you by Dirichlet test, right? This is your convergent, is not it? This is your convergent. Now suppose coming to this integral, what will happen here? Here p is equal to here 1 here, x to the power 1, is not it? P is equal to 1 here. P is equal to 1 means this is p greater than 1 convergent, means this integral is divergent here. If you want to evaluate it, so this is equal to your limit lambda tends to infinity. This is log x, right? It is 1 to infinity. So log infinity is infinity, means it does not exist. If it is asked to evaluate it, does not exist, is not it? Similarly, coming to your 6, you see the limit is here 0 here. So we need to split it. Some integral say 0 to some constant a, right? A is positive, or particular if I take one, no issue, then it is sin x by x plus integral 1 to infinity sin x by x. So this is again the second type will come out here, because this 0 is here in the denominator. But anyway, limit x tends to 0, sin x by x is 1 here. So this will give me a finite value. This will give me a finite value, and rather I should split it here. I should split it here to have the Dirichlet test here. So here 1 to infinity 1 by x into sin x, right? It is my phi, it is my f. So this is decreases gradually. When x increases, this will decrease. So f is decreases and bounded, right? And we see integral phi dx, right? Integral phi dx a to x, right? This is also some less than constant as we did earlier, right? Is less than constant. So the second part of this integral is convergent by Dirichlet test. So now this and this together will give you convergent. So this integral is convergent. In fact, the value of this integral, is pi by 2. This is called a sine integral. Okay. So you later on know that how this integral becomes sine pi by 2. It is only pi by 2. By your complex counter integration also you will get it pi by 2. Now my remark is here. Phi and f, anyone, right? You choose. choose phi and f as per your convenience, right? You may interchange it, no issue, right? But we have to see the conditions here. So this Abel test and Dirichlet test are the wonderful test to deal with the product of non-algebraic function, non-algebraic slash algebraic functions, right? Slash algebraic function, right? So in this way, we will able to evaluate the integral of the first kind. In our future lecture, we will see the improper integral of second kind. The video is getting lengthy, so I want to conclude it here. Thank you all.